In this question here, we are told that a 500 Newton student experiences an upward acceleration of 2 meters per second squared, a downward acceleration of 1 meter per second squared, and motion at constant velocity. And we are asked in part A to explain when each of these three situations occur. Okay, let's pay attention to what the question says. During part of an elevator upward ride. So that's important. The elevator is moving up. The 500 Newton student experiences an upward acceleration of 2 meters per second squared, downward acceleration of 1 meter per second squared, and motion at constant velocity. So the three situations. So when do we have upward 2 meter per second squared acceleration? Upward meaning the acceleration is going to point up. In the case of this question, since the elevator is moving up the whole time, the velocity of the elevator is pointing up the whole time. So we have an upward acceleration when the velocity is increasing or when the elevator is speeding up. Remember, whenever velocity and acceleration are in the same direction, we conclude that the velocity is increasing. What about downward? One meter per second squared. The velocity is still up, but in this case our acceleration down. Remember, whenever the acceleration is opposite in direction to the velocity, our object is slowing down. So in this case, the elevator is moving up but slowing down. The constant velocity situation is the easiest of all three. That's just simply when the elevator is moving at a constant velocity. Now, part B of the question is asking us about the apparent weight of the student during each of these situations. Okay, now to think about the apparent weight, we need to think about what's going on here. So this is the person, the student, inside the elevator. What are the forces acting on the person? The forces acting on the person, no matter how the elevator is moving, are the gravitational force due to the earth pulling down on that person, and the normal force exerted by the floor of the elevator on the feet of that person. That's the only two forces acting on the person. The sum of these two forces, according to Newton's second law, Fg plus Fn, should be equal to the mass of the person times the acceleration of the person. There is one caveat here. The acceleration of the person is the same as the acceleration of the elevator. Now, what do they mean by the apparent weight? If the person was just fallen, even though he's subject to the gravitational force, that person is feeling weightless. But then, if they are standing in an elevator or in a room, they are not going to feel weightless. So what's going to make the difference? It's the normal force. So that's why the normal force is what actually makes you feel heavy. and that's what we are referring to as the apparent weight here. So when they are asking about the apparent weight, they are asking us to find the normal force. If instead of the floor, we have a scale there at the bottom of the elevator, that's what the scale reads, the value of Fn. So let's continue this in the next page. So we have three situations. Upward acceleration of 2 meters per second squared. Remember, we just said that Fg plus Fn is equal to ma. Now in this case, taking the upward direction as positive, so minus m, the mass of the person, times 10 newtons per kilogram, I'm using that for simplicity instead of 9.8, plus Fn, that's going to point up, is equal to m times plus 2 meters per second squared, since a is pointing up. So that gives us, in this case, our Fn is equal to m, moving this to the other side, m times 10 newtons per kilogram plus 2 meters per second squared. Remember, newtons per kilogram and meters per second squared are equivalent in units, so it is just m times 12 meters per second squared. So we need to know the mass. If we go back here, they tell us the person has a weight of 500 newtons. Whenever it's in newtons, that's the weight of, or the gravitational force on that person. So to get the mass, it's going to be just Fg over g, using 10 for simplicity. That gives us 50 kilograms. So in this case, our Fn is 50 kilograms times 12 meters per second squared, so that gives us 600 newtons. Quite a gain in weight. Now, in the case when we have a downward acceleration of 1 meter per second squared, the direction of the acceleration is negative in this case. Looking back at this equation, we still have minus m times 10 newtons per kilogram. Fg is still pointing down, Fn is still pointing up, so that's positive. That's equal to m times minus 1 meter per second squared. That's the difference. The minus, remember, is because the acceleration is pointing down. So in this case, that gives me Fn is equal to 50 kilograms times 10 Newton per kilogram minus 1 Newton per kilogram, which is 9. So that gives us 450 newtons. When the elevator is moving at constant velocity, then the acceleration is 0, and Fn in that case is just equal to Fg in magnitude, so which is 500 newtons.